Okay, so let's get started with the week 5 of electromagnetics in guided and wireless media course, which is being offered on NPTEL portal. And I'm Shazam Bhatt, and I'm working at TU Berlin and Paul Drude Institute, and I'm associated also with IIT Bombay. So this course is being offered by Professor Pradeep Kumar from IIT Kanpur, and uh, I should say he's a great teacher who is well renowned in the field of electromagnetics, high frequencies, and electromagnetic waves and wireless communications. So, what we are going to do today is just give me a moment. Okay, so sorry for the interruption. So what we are going to see today is we are going to solve certain problems, which will be basically share the screen first, which will be related to the topics that you might have covered in week 5. That might include the movement of electromagnetic waves in guided media, which is basically dielectric slabs. You might have talked about total internal reflection, critical angles. You might have seen about certain modes which are basically supported by the waveguide. So you have talked about basically solving the Maxwell's equation in dielectric slab, or what sort of a modes are basically supported in a dielectric slab, whether uh, these can be TE modes, TEM modes, or all other sorts of modes which are basically being supported by the dielectric media. So you have talked about all of those phenomena in this week, so I'm not going to again go through these. What we are going to do today is to directly jump to solve the problems, and in between, whatever important concepts or the things that are essential for understanding those concepts, whatever they will be, I will be try to just briefly brush up those concepts, but mostly it will be then focused towards the questions, and we'll try to briefly analyze what sort of other effects can we correlate with the with these courses which you have basically uh, done with the part you have done in this week. So that's the fundamental thing which we'll be trying to do in this session. So let me just reconnect it from the device and just okay. So now going directly to the assignment 5 problems, which are some sample problems, but they are essential for you to basically understand certain concepts, and these will be important for your from your even exam point of view and for your understanding point of view. These are really going to be essential for both of these. So that's why I will try to discuss the concepts in between whenever the need arises. We will be trying to basically uh, revise those concepts. So taking the first question directly, so you might have seen that you have studied about the total internal reflections. You have studied about at what particular angle, if you incident the wave, it gets reflected internally inside the medium. So the question here says for the first question, you have a glass air interface which is having the refractive index of 1.5. This is for the glass, this is for the air. Assume the incident wavelength is this. So this is the incident wavelength, and the angle of incidence is given, which is 60 degrees. At x naught is the distance in which the field reduces by a factor of 2. So this is an important information. So they say that you have, let's say this is a glass slab and this is the air. Then you have the glass air interface, and this is the refractive index of glass, which is N1, and this is N2, which is for the air, which is equivalent to 1. And the incident wavelength is approximately 6 into 10 to the power minus 7. So incident wavelength is around 600 nanometers. Okay, and the angle of incidence is given. So as per the refractive, as per the, even when they are mentioning that this x naught is the distance in the rarer medium, you know that glass is a denser medium. This is a rarer medium. Okay, so basically you have the incoming electromagnetic wave that is getting hit at this interface, and then it will get reflected depending upon, or it can get transmitted depending upon what is the angle. But that is the point we are basically about to find. We need to find the critical angle at which basically it will come back into the glass interface. That is basically the critical angle. So, but the problem here is that the incoming electromagnetic wave is around, the wavelength of this is 600 nanometers. Now, what happens when it hits this particular interface? It If it hits at a particular angle, which is basically the critical angle, then it gets back into the glass slab. But despite the reflection, there is always the some leaking part of the wave which gets leaked into the basically external medium, no matter how much the reflection is. So this is basically something called as leaky part. Okay. So if it's something like this, if you have, let's say, if you have basically a waveguide, something like maybe this, if this is a waveguide, then this is like a waveguide slab. Let's say this is the substrate, and you have the electromagnetic wave which is moving in this slab. And you know from Maxwell's equation, if you solve the Maxwell's equation, you get different modes. And what are these modes? These are just different electromagnetic waves, the solution of Maxwell's equation that is supported by the slab. Okay, and once you solve it for different modes, you basically you get different solutions of Maxwell equation depending upon the boundary condition of this slab. Okay, depending upon the boundary conditions of this slab. Now, when you solve it, you get the first solution of Maxwell's equation, which looks something like this. It's like a Gaussian packet which propagates in this slab. Okay, so as it propagates in this direction, which is the z direction, so it propagates and it decays with the z direction. And depending upon how long the waveguide is, accordingly you will get the wave propagating in the slab. Okay, but you notice that this Gaussian wave packet also extends out of the slab. So this is something called as leaky part of the of this particular mode. So this is sort of a leaked into the external medium. Okay. Now the similar phenomena happens when the reflection takes place. You always have certain, if you let's say irradiate if you irradiate, let's say if this is medium 1, this is medium 2, and you have incoming electromagnetic wave, it gets reflected perfectly, but there is always some leaking part inside, which that basically goes inside the medium. So if you have, let's say, the wave coming in like this, then it will get reflected like this with certain phase change. But at this point, it slightly leaks into this medium. So this exponentially falls. And this distance up to which it exponentially falls is in different contexts is sometimes called as skin depth. It's sometimes called as absorption depth. It's sometimes called as, I mean, there are different terminologies for it. So this is a similar question here. And once we solve it, there's more into this particular phenomena once we solve it. So what we are basically trying to see now, we need to see that once this wave decays, exponentially out of the medium. Let's say it decayed up to this part or some part, which is basically x naught, then we need to find at what x naught does this electromagnetic field drop by a factor of 2. So we need to find this x naught at which the field or the intensity, whatever, at which this amplitude of the field falls by a factor of 2. That means if this was the amplitude, let's say I, then we need to find x naught such that the intensity or amplitude becomes I by 2. Okay, so that's the problem which we need to solve. And we need to find the critical angle as well, and we need to find x naught also. So this is a problem which we will take, let's say, which we will take here. So you have this, you have incoming electromagnetic wave, and you need to find the critical angle. Okay, so this is 600 nanometer wavelength. This is N1, this is N2, this is glass, this is air, and this is the leaking part of it. So we need to find X naught at which the intensity or the field falls by a factor of 2. Okay, we know that if you apply Snell's law at this interface, so this is the solution, how you can approach basically the solution of problem 1, solution for question 1. You are given the N1 is basically 1.5, N2 is 1, and you are given the wavelength is 600 nanometers, and incident angle is also given as 60 degrees. You know that if you apply the Snell's law at this particular interface, you can basically write the critical angle to be equivalent to sine inverse of N2 divided by N1. Okay, and if you solve this, you get this approximately sine inverse of, which is basically 1 divided by 1.5. So you can write it as sine inverse of, this is 2 over 3. So this is approximately 41.8 degrees. So this is the critical angle at which this will go back into the glass slab. Now, what else we need to find? We need to find this distance x naught at which intensity falls to, or field, basically field falls to I by 2. And for that, what we need is basically absorption coefficient, which is basically attenuation coefficient. That how much the wave attenuates once it hits this particular interface, once it hits this interface, how much the wave attenuates. And that is quantitatively captured by this attenuation coefficient value. Okay. So attenuation coefficient, you know that you can write attenuation coefficient as the frequency over C and 1 sine of incident angle. Okay, and you know everything, you know this is 2 pi nu over c and 1 sine theta I, and everything is given. I guess you have the wavelength as c over nu, so this will be 2 pi over lambda n1 sine theta I, and essentially what this is basically, this is alpha equals to k times n1 sine theta I, where this k is basically the propagation vector or whatever you call it. It's sort of a equivalent to 2 pi by lambda. Okay, and once you have it, you just need to put the values 2 pi into 3.1415 over 600 into 10 to the power minus 9. You have N1 as 1.5. Remember, this N1 is for the glass, not for the air. Don't get confused here. Most of the time, students take this as N1 and this as N2, which is absolutely wrong. You just need to see the order of in the question. This is glass-air interface. So this will be glass, this will be air. And it is naturally, you know it, because for air, the refractive index is 1. For the glass, it's 1.5. But if it would have been written as air glass interface, then it would have been given as n1 equals to 1 and n2 equals to 1.5. But that's not the case here. It's written something like this. So sometimes the glass air interface will be replaced by some other interface. Let's say they will write glass oil interface, and they will write as n1 equals to 1.5, n2 equals to, I don't know what is it for oil, maybe 1.9. I'm just giving the rough values. Then this will be for this will be for oil. Don't get confused. And if they write oil glass interface, it basically means, I mean, N1 will be 1.9, N2 will be 1.5. So just consider these values. And this is really important because It also tells you from where to where is basically the electromagnetic wave. Where is the electromagnetic wave coming from and where it is going? So that's also essential. Okay. Now, if you solve this, what else you need into sine of theta incident, which was basically 60 degrees. You solve this, you get alpha to be equivalent to 1.36 into 10 to the power 7 per meter. Remember, the unit is per meter. Why? Because this is dimensionless. K has a unit of per meter. So it's basically radians per meter, but let's take it as per meter. So you have found the attenuation coefficient now as 1.36 into 10 to the power 6. Now, you know what this attenuation coefficient is? It has a unit of per meter, but if you take an inverse of attenuation coefficient, that will be in meters. And this exactly gives you the details that basically something called as attenuation depth, or in other terminology, in optics terminology, it's called as absorption depth. Okay, so how much got absorbed, or basically absorption, how much is the absorption depth of this particular electromagnetic wave? If you take the inverse of it, it's not exactly inverse, it's basically the value. Let's say if you have intensity versus x curve, and intensity at this point is I naught, then once, and this is, let's say this is some medium 1, and this is medium 2, and intensity in the medium 1 was I naught, and then when it hits the medium 2, it drops exponentially. Okay, and this is exponential decay. E to the power minus, it drops e to the power minus alpha x, alpha x. Okay, so this absorption coefficient exactly captures that at what x value, the intensity becomes 1 by e of the initial intensity. Okay, so that is basically the absorption coefficient. At x equals to alpha, the intensity becomes 1 by e times the I naught. So intensity drops to 1 by e. That is exactly absorption coefficient. That means this is going to give us the information at which the intensity falls. Now, you know that if you have that means, for example, the this decaying part, which is decaying out into the air, which is decaying out into the air. In other terminology, some terminology, it's also called evanescent modes, evanescent decay. It's just a name. Just don't go through the names. It's just a name, evanescent decay. Okay, and we need to find the distance x naught at which the field drops by 2. So you need to find x naught at which the field drops by 2. That means at which the field becomes half. That means you have e to the power minus alpha x naught to be equivalent to 1 by 2. That means the intensity basically drops to 1 by 2. So you can write x naught to be equivalent to ln of 2 divided by alpha. And this is the exact thing you need to obtain. So you have alpha. So x naught will be equivalent to ln of 2 divided by how much was alpha? 1.36 into 10 to the power 7. This will be meter. So this will be per meter. Meter will go up, so it will have the units of meter. So you solve the x naught, you get 51 nanometers. This is the exact answer of this question. That means the electromagnetic wave was coming and it started to leak out of the medium and then it got reflected. And this leakage, at which the value of intensity dropped by half at x naught equivalent to 51 nanometers. That means if you measure this, and this is 51 nanometers, and you measure the intensity at this point, it will be dropped by half. Okay, because it's exponentially decaying outside the medium. Now comes the interesting part. What happens if you bring something close to this decaying part? So this is the evanescent, sorry, this was an issue. So this is the evanescent decaying part. Okay, and oh, now what happens? Let's say if you if you bring something very close to this decaying part. Let's say you bring in something, let's say this is 51 nanometers. Let's say you bring in something very close to this 51 nanometer region. You bring it so close to the glass slab that this distance is less than 51 nanometers. Okay, what is going to happen? Essentially, what will happen that because it was still decaying, it is going to decay through this particular medium also, and then it will propagate through the medium as well. That is the beauty of this. That means you are going to couple the leaky part or the evanescent decaying mode, and you have coupled that. This is basically coupling of the evanescent modes into this particular medium, and it will propagate in this medium. How it will propagate, that's a different story altogether. But it's going to propagate obviously because it's a wave, then it will come here, then it will propagate as a wave, but with a decaying amplitude because its amplitude was already decaying. So this is something called as tunneling. So this is basically tunneling. That means the wave has basically tunneled through this region and it has gone into the other medium. And the important part is that this tunneling you might have heard in electronics. You might have heard it a lot. The electron tunneling or something called as quantum tunneling. Quantum tunneling. This is quite famous and recently Nobel Prize was also awarded for, but that is a different quantum tunneling. That's not a same tunneling, that's a different story. But in electronics, this quantum tunneling is often studied in even undergraduate courses, in electromagnetics, in device physics courses, semiconductor device courses. That is exactly the same phenomena there. And what happens in electronics is that if you have a potential something like this, if you have a potential, this is basically potential of this is the electrostatic potential V naught at this particular point. Let's say this is 0 to A, and this is X direction. That means let's say you have certain atom here, maybe a negative charge. A negative charge because of which the electrostatic potential goes up here at this particular point. So this profile is basically showing the electrostatic potential. Okay, now let's say assume an electron is basically coming to hit this potential. When the electron comes, it hits this potential. There are two things that can happen. Either this electron will get reflected of this because of this potential, or something bizarre can happen. It can basically tunnel through this potential. Okay, and that is something called as quantum tunneling, and that is a similar phenomena. It's essentially the similar phenomena because the electron was here is coming as a wave, and once the electron as a wave hits this particular barrier, which is basically a potential barrier, it starts to decay. And if you reduce this width of the barrier to a smaller value, if you reduce this, you will see that the decaying part will leak and it will go to the other side, and you will see the electron on the other side. And this is something called as tunneling. And this is the same phenomena because it's a wave, because electron is a wave, and because the wave has now decayed. So this is the exact same thing called as evanescent decay or evanescent decaying part, and it leaks to the other side of the barrier, and you get the electron on the other side. But if you make this barrier to be large, something like this, if you increase this from 0 to 2a, then what you're going to see is that if the electron is coming here, it's going to leak and it's going to decay, and you're not going to get anything here. And that is the same story which exactly I've told you here. So once you have the wave coming in and it is decaying and its amplitude is falling to I by 2 at 51 nanometers. If you bring something very close to the 51 nanometers, it's going to leak into that medium, it's going to come out in the medium with the reduced amplitude. That is the concept of tunneling and evanescent decay. Okay, but here you solve the Maxwell's equation because these are electromagnetic waves. But for the electrons, what you solve is basically here the Schrodinger equation. You solve the Schrodinger equation that gives you the decay of electrons wave function. Okay, wave function which is represented as psi as a function of x because this direction is x. But the wave function is also a mathematical function similar to what you get here. It's a mathematical function which is basically moving electromagnetic wave e to the power minus I kx minus omega t. So similarly, you represent this wave function in this region as e to the power minus I kx minus omega t. It's like sort of a plane wave which is moving, and here you have a solution of something like e to the power minus alpha x, and then again here you can, if it leaks, you have a solution of e to the power minus I kx minus omega t, except that the amplitude factor will be reduced by 2. That is the same thing. I mean, the story is same, the mathematics is same, and the concept is same. Okay, so that's about this question. I think I went deeper into it, but that's the story about it. Now, and it's not sort of a theoretical story, it's all mathematically based. Once you solve it, you get the solutions which are exactly same. So that's why most of the times when I started this course, I told you that this is all about waves. If you have understood waves, you have, I guess, understood half of the electronics, I guess more than 50% of the electronics and semiconductor physics and electromagnetic waves, and most of the electrical engineering is based on waves. So that's about it. And now that means the answer of this question is going to be this part, which is basically 51 nanometers, and the 41.8 degrees is basically the uh, angle of critical angle. Now, in the exact same question, we need to find the phase shift for the reflection at the glass air interface. Now, there is one more aspect that once the electromagnetic wave is coming, it is getting hit and it leaks, some part of it leaks into the rarer medium, and most of it gets reflected. And you know that at this point, reflect when the reflection occurs, there is basically a phase shift which is noted as phi. So we need to obtain this phi phase shift, and I have talked about this reflected reflection based phase shift a lot in the previous sessions. So we need to find this particular phase shift, which is basically happening. So you have an incoming wave, you have a decaying part. This is basically the normal to the surface, and this is the incoming electromagnetic wave. And then at this point there is some phase shift, and it's going coming back here, it's getting reflected. So if this was theta incident, then this is basically the phase shift, the phi which we need to obtain. This is basically 2 phi because this is composed of this part and this part. Okay. Now, how you can find this? Oh, sorry. How you can find this particular phase shift is that you simply write it in terms of, I should say, you can write 2 phi in terms of the trigonometric identities. You can write it in terms of 2 times tan inverse of u over cos theta inverse, where this u is basically dependent on refractive index, which is n1 squared divided by n2 squared under root of sine squared theta incident minus sine squared theta critical. So that's basically the dependent upon critical angle. And you need to find this 2 phi. That means you need to find u. Everything is given. You have the incident, you have critical angle. U will come out to be approximately 1.2245, and you can use it. You get 2 phi to be equivalent to 2.4 radians approximately. And that means the phase shift is basically around 2.4 radians, which is very small, but you can understand it from the wave phenomena as well. And you can even convert this 2.4 radians into the degrees in order to see how much degree of the phase shift is basically happening. So that's the essential part about this question. And and if you can relate it basically with this particular phenomena, even it happens with the electrons. So when the wave is coming, electrons wave is coming, it hits this medium, it decays into the medium. But what happens is that if it decays and it doesn't appear on the other side, then obviously the wave is going to get reflected, and it reflects with the opposite phase. Okay, with almost with different phase obviously, and it reflects in the opposite direction. If it was moving like e to the power minus I kx minus omega t, or e to the power minus I omega t minus kx, then this part will be like e to the power minus I omega t plus kx, which is in opposite direction, minus x direction. So this was in plus x direction. And that's the similar thing which basically happens with the optical waves as well. So the essential thing is that the answer for this question will be around 2.4 radians at the glass air interface. Now, what else is there? Other questions are mostly based, sort of formula-based questions, but let's go through them and let's discuss. So you have question three, and you have a dielectric slab waveguide with constitutive parameters as dielectric permeability is mu naught and dielectric permittivity is 2.5 times the permittivity of free space. It's situated in free space. What will be the minimum thickness of slab so that these TM and TE wave of the even type of frequency 20 gigahertz may propagate along the guide? So you have a dielectric slab and its parameters are that this is mu naught and this is 2.5 times epsilon naught. It's situated in free space. We need to find the minimum thickness. Let's call the thickness as D, so that TM or TE wave of the even type at a frequency 20 gigahertz may propagate along the guide. So we need to find the minimum thickness so that this sort of a wavelength or the frequency 20 gigahertz, which is approximately how much will be the wavelength. It will be speed of light divided by frequency because it's in free space, so it'll be speed of light divided by the wavelength. So it will be 3 into 10 to the power 8 divided by 20 into 10 to the power 9. So accordingly, you get the wavelength value. So we need to find the minimum thickness so that it can support the wavelength. And why this TM and TE wave only? Because this slab, which is basically a dielectric slab, it cannot support the transverse electromagnetic waves. And why it cannot support is because of the boundary conditions, which comes from the Maxwell equation. In order for you to have a transverse electromagnetic wave, that means EZ component 0 and HZ component 0, and the wave propagating along Z direction, let's say this is Z, that means you have E perpendicular to H perpendicular to Z, that is basically the transverse electromagnetic wave. And in order for this to happen, you should have two different surfaces altogether, which will basically support different. So that basically you should have two different polarities. So that, for example, if you have a slab like this and if you have a slab like this, you should have basically two different set of conductors so that the electromagnetic wave can flow. So because you only have a only single sort of a conductor here or a dielectric, whatever you call it here, that's not going to support the transverse electromagnetic wave because it cannot support the perpendicular component of the electromagnetic wave in it. So that's, I mean, if you are really interested in understanding why TEM mode cannot propagate in a dielectric slab, you can just look for it in some of the books because it has a deeper explanation that goes into the boundary conditions and comes from solving the Maxwell's equation. Okay. But essentially, you need two different planes with different set of polarities in order for it to support the transverse electromagnetic wave, which is basically something like this. This is the E field, and this will be the magnetic field, and this will be the Z direction. So this is exactly transverse electromagnetic field, and it cannot propagate in a dielectric slab waveguide. Only TM or TE waves can propagate. And what is TE mode? That means it is the E is perpendicular to Z and the H, the EZ component is zero, but EZ component is zero, but HZ component is not zero. And for TM, the HZ component is zero, but EZ component is non-zero. And these waves can exactly propagate in these sort of dielectric slabs. Now let's go back to we need to find the minimum thickness that is going to support this particular wavelength or frequency. For that, what we are going to do first, add a page, and then we know that if you have this is basically the solution 3. You know that the lowest TE and TM modes of the wave, that they have the same cutoff frequency along the dielectric slab. So you know, you might have seen in the lectures. So if you refer to the lectures, the cutoff frequency is basically given by n minus 1 by 2 divided by d under root of mu d epsilon d minus mu naught epsilon naught. This is the cutoff frequency or cutoff wavelength. So for the in the question, if you see, so for, let's say, if you use for n equals to 1 for the first n equals to 1, you have the cutoff frequency to be equivalent to C divided by 2d under root of mu naught mu d epsilon d divided by mu naught epsilon naught minus 1. Just take this out, and accordingly you can get d from this, which will be basically 2 divided by C divided by 2fc under root of mu d epsilon d divided by mu naught epsilon naught minus 1. Every detail is given. I guess mu d is equivalent to mu naught, epsilon d is equivalent to 2.5 times epsilon naught, and you can put the values here. This is 8.85 into 10 to the power minus 12 farad per meter, and this is 4 pi 10 to the power minus 7. And once you solve it, you get d minimum to be approximately equivalent to 6.12 mm, 6.12 millimeters. And that is the value of d minimum that is basically going to support this sort of a frequency of, how much was the frequency, by the way, of 20 gigahertz. 20 gigahertz. And how much is the wavelength corresponding to it? It will be 3 into 10 to the power 8. In free space, it will be 20 into 10 to 10 to the power minus 9. So this will be 3 by 20 into 10 to the power minus 1. So this will be 3 by 2 into 10 to the power minus 2. It will be 1.5 into 10 to the power minus 2. So this is approximately 1.5 mm. 1.5 mm. Okay, so I'm just calculating it. This is not asked in the question. So this is the free space wavelength. Okay, just cross-checking it. Okay, so now moving on to question. This was question 3, so it will be around 6.12 millimeters. You see that this cannot be the answer. It cannot be 29 micrometers, because if it falls to a value which is less than the wavelength, if you computed the wavelength earlier, and if it falls less than the wavelength, then you pretty much are below the, I should say, diffraction limit. And it's not going to be possible that you can propagate a wavelength of, let's say, how much was it? Of 1.5 millimeters. It's not possible that you can propagate the wavelength of 1.5 millimeters in, did I compute it correctly, by the way? Yeah, 1.5 millimeters. Yeah, it's not possible for you to propagate 1.5 millimeter wavelength in a structure that is 29 micrometers. That means the structure will be this, or whatever. The structure will be to this 29 micrometers, and the wavelength is greater than 29 micrometers. So this is not possible. The structure size has to be of the order of wavelength or greater. Otherwise, it goes into the diffraction limit, which goes into a different regime altogether. So, uh, so this is about this particular question. Now, moving on to question 4, consider step index planar waveguide with thickness of 3 micrometers. So you have a step index planar waveguide. So what is a step index? It means, what did I drop? Step index basically means that you have a step in a refractive index. Refractive index. What does it mean? First, let's read the full question. So this is the thickness, which is given as, let's write the thickness as D, which is 3 micrometers. And refractive index is 1.5. Let's write it as N, slab as 1.5. Surrounding refractive index is 1.49153, and the wavelength is 1.5 micrometers. We need to find the V number. So basically, V number gives you the information of how many modes are supported by the waveguide. And modes are just the solutions of the Maxwell's equation. Maxwell's equation. And what is exactly it? So basically the question is about step refractive index. That means if you have a structure like this, let's say this is a substrate, let's say this is a substrate, and you have some other slab on it, which basically looks like this. Let me draw it with a different color. Oh God. So you have a slab on it, and you want to propagate your electromagnetic wave via this dielectric slab. Now you see that what is basically happening is that there are it has a refractive index gradient. So if this is x direction, then if you draw a plot of refractive index as a function of x versus the x, what you get is basically up to this point you have one refractive index, and at this point exactly, I mean, for the blue region you have a different refractive index, and for the red region again you have another refractive index. So that means you have a refractive index profile that looks like this. So this is called a step index, or step index of the step index waveguide. That means refractive index at this point was, let's say, n1, here it is n2, here it is n1 again. As a result of which, what basically happens that when your electromagnetic wave comes, it sees two different refractive indexes. You try to localize the electromagnetic wave in this region, but obviously you have an electromagnetic wave that is coming, it's going to see the refractive index. And once it sees the different refractive index, it always propagates via this index, which is greater, which is n2. So that's why it tries to propagate in this region. Okay, it tries to propagate in this region through this particular slab. Now, what exactly is being asked, and what does it mean to the what do the modes mean? So now you have the index in the refractive, you have the step in the refractive index. So what you do, you solve the Maxwell equation for it, for basically the electric field and the magnetic field. But particularly, let's consider electric field here first. Let's ignore magnetic field for some time. When you solve the Maxwell's equation, and you get some certain solutions, and most of those solutions are in terms of, I guess, legendary polynomial functions, legendary polynomials. Okay, what are those? These are just mathematical functions which basically represent certain variations of the field in space and time. Okay, so you get some e as a function of x comma t. That's as simple as that. When you solve it, you get different solutions, and you know how the first solution looks like? It looks like something like this. And if you solve it for the second solution, I'm just drawing it here. It will look something like this. I will show it here. If you solve for the second solution, it will look something like this. If you solve for the third solution, it will look something like this. If you solve for the fourth solution, it will look something like this. So these are different solutions of the Maxwell equation, and it shows how the, oh, what happened? God. It shows how the electric field oscillations are taking place in it. Basically, electromagnetic field, well, let's consider electric field oscillations here, but it's actually electromagnetic field. So it shows these oscillations, how these are basically oscillating in space in the waveguide. That's about it. That's it. It doesn't mean anything much more than this. And now if you let's jump to the question and then discuss more about it. If you have to find that how many of these modes, so basically these solutions which look like this, the mode 1, which is solution 1, mode 2, mode 3, mode 4. So these are different modes, and these are different solutions of the Maxwell equations. So these are basically electric field oscillation as a function of space. So this is x, this is EA as a function of x, and this is the amplitude of the electric field. So these are the amplitudes of the electric field. Okay. And and exactly this V number quantitatively covers this particular thing. It shows that how many of these modes are basically supported. And this V number you might have seen is mathematically given by 2 pi over wavelength times d under root of n1 square minus n2 square. That this is basically k, which is basically the wave vector or propagation constant. You have everything in your hand. You are given everything. You have 2 into 3.14 divided by 1.5 into 10 to the power minus 6 meters, which is basically wavelength, into 3 into 10 to the power minus 6, which is basically the thickness of the slab, under root of n1 is basically 1.5 square minus 1.49153 square. So when you solve it, you get V to be approximately 2. That means two of these modes will be supported. That means it can support this mode and it can support this mode. No, that's as simple as that. That means the electric field oscillations or the variations in this waveguide can look like either this or it can look either this, and they are basically simultaneously happening. It's sort of a different uh, the electromagnetic wave will propagate in the form of these profiles in space inside it. Okay, so that's the detail about it. So you have the answer as two. If it was infinite, that means it would have supported all of the solutions of the Maxwell equation, all of the modes, but that does not happen in realistic situations. Most of the time, it supports few modes, not exactly one mode, but it supports multiple modes. So for that, you have to do mode engineering. You have to make it support only a selected mode so that that can propagate basically through this waveguide. So now you understood this question by considering the refractive index gradient as a function of x. Gradient means variation of this as a function of x. Now, a similar sort of analogy happens basically in electronics. And in electronics, we are talking about electrons. And when we're talking about electrons, we are talking electrons as a waves, which has certain wave function, and that wave function can be obtained by Schrodinger equation. And what does wave function give you? Wave function is a function of time, space and time. And it exactly tells you the probability of finding an electron in space and time t. Okay, so this is about electrons in electronics. Now, how can we relate it with electrons? You know that you have certain structures. You have, let's say, if you have material one, let's say this is material one. Let's say this is let me call that let's say this is a material one with a band gap which is around, maybe let's call it 1 electron volt. Band gap is basically this. If this is a conduction band, this is the valence band of a, let's say this is a semiconductor. You might be knowing about it. Then this is exactly the band gap of it. And this is, let's say, material one of some band gap 1 electron volt, and this is material two of another another material of, let's say, band gap of zero point 0.5 electron volt. And then you have again material 1, then you have material 2. These are repeated, 1 and 2 are repeated. You have material 1, material 2, so on and so forth. So you have a layers of materials. You have layers of these different semiconducting materials. But the essential point here is that when you draw the band diagram of it, you might be knowing about the band diagram because this is an advanced course. So you might have studied in your undergraduate courses about the band diagrams. The band diagram for the first, this is the conduction band of first, this is the valence band of first, and this is the band gap. It will be greater, it will be 1 electron volt, as I just took an example. So this is, let's say, as an example. And for the second, the band gap will be lower. For the first, again, it is here, for the second, and then it's repeated. So once you join them, you get something like this. You get something like this. And then it repeats. It repeats. So here it's again like this, and then this. So it repeats. So essentially, what this band diagram tells you, these are basically potential energies of an electron. That means if this is the conduction band of first material, and this, oh sorry, second material, and this is the valence band of second material, this particular thing, and if the electron is here, it the band diagram or this bands basically give you how much is the potential energy of the electron at this particular point. Okay, and now what is basically happening is that you have a potential gradient. So you have a potential gradient here. So basically you have a step potential gradient because of different layers. So this is sort of a something like this. This. These are different steps in the potential, electrostatic potential, electrons potential. So that means the potential electron is gonna feel is basically going to be different in each of the layer because of the different electrostatic potential, because of the step potential. Okay, now what? Now the point is, if you do some band engineering and if you make these regions, which is basically the second region, if you make these regions the the length of this region of the order of electrons wavelength. And how much is electrons wavelength? It is basically the de Broglie wavelength, which you might have studied in class 12th or class 11th, I don't know. And de Broglie wavelength is basically h over its momentum, and you can basically compute it using the uh, energy of electron, the mass of the electron. I guess it's h over under root of twice m into electron's energy. If you somehow make this length of the order of electron wavelength, and if you compute it will be different for different systems, but let's say electron wavelength comes out to be of the order of 5 nanometers. And if you exactly make this length as 5 nanometers, what you're going to see is that if the electron is here, it will not be as a particle, it will be wave, because the length is of the order of wavelength now. And once the electron is as a wave in this particular region, so you need to solve Schrodinger equation to get the wave functions. Once you get the wave functions, those are a function of space and time, and they tell you the distribution of, or the probability distribution of electrons. Once you solve it, so once you solve the Schrodinger equation for this system, which is a graded potential. So for example, you had this was material 1, this was material 2, 1, 2, so on and so forth. So you had an energy level. This was conduction band for second, this was conduction valence band for second. You had an electron here. You solved the Schrodinger equation. So beauty is that once you solve the Schrodinger equation, you get the solutions as a wave function, and they are basically the solutions with different modes, similar to the modes in the Maxwell's equation that gives you the modes of the electromagnetic waves through the slab because of the gradient in the refractive index. This is the gradient in the refractive index. This is the gradient in the electrostatic potential. But the solution which comes because of solving Schrodinger equation that gives the wave function that gives you different modes, which are basically the supported electron waves in the graded potential. It is exactly the same. I mean, the solutions, when you see the solutions, it looks something like psi as a function of x. Let's forget about time dependence right now. It looks something like amplitude sine of n x divided by L, n pi x divided by L. So it's basically a sine function, and when you solve it for different n, for different n equals to 1, 2, 3, 4, so on and so forth. So basically for different modes, when you solve it, you know what you get the solutions? You get solutions as this is n equals to 1, n equals to 2, n equals to 3, and what you call in electronics these as energy levels. These are different energy levels where electron can stay. And when you see the solutions are basically in n equals to 1, it looks something like this. In n equals to 2, it looks like this. In n equals to 3, it looks like this. If you go higher and higher, n equals to 4 will look something like this, so on and so forth. And this is exactly the similar as the electromagnetic waves propagating through the dielectric slab. So that is the beauty. If you have understood the electronics or the electromagnetics, that is the same set of a solution which basically resembles because both are waves. And the and this particular thing here, which is basically these oscillations, it is basically showing the oscillations in the wave function of an electron as a function of x. That means if you take if you take, let's say, one of these regions, and you have n equals to 1, which is basically first mode. So this is basically telling you the psi as a function of x. And psi as a function of x, if you square it, this is called as probability density function of an electron. And it tells you exactly that at exactly this point there is a maximum probability of finding the electron because it's peaking at this particular position. But if you go to, let's say, n equals to 2, and your probability distribution looks like this, that means there is a maximum probability that you can find the electron here, or it will be here, or not here. It will be either here, or it will be either here. That is basically showing you the how much where is the probability of finding the electron maximum, because these are the wave functions. But in here, these particular things are electric field amplitude as a function of x, and these are basically showing you at what points the electric field amplitude will be maximum. It's not that at what point the photon's probability will be maximum. That's a different question, but this is basically showing at what point the electric field amplitude will be reaching the maximum value and how it will be varying in space. Because you're solving the Maxwell's equation for electric field and the magnetic field, but you are solving the Schrodinger equation for a wave function, which is basically the probability distribution of the electrons. But the solutions are exactly same, the mathematics is same, the physics is same, the essential idea is same, and because these are waves. I've been telling it from point first lecture itself. Okay, so I think I went into a deeper discussion about it. So let's forget about it now, and let's move on with the question. Now, if we have question 6, sorry, question 4 we did. Now, the cutoff wavelength of a step index fiber is quoted as 1.2 micrometers. If the fiber is operated at wavelength of this, what is the V number? Again, we need to find the V number. And it's for a step index fiber which has a refractive index gradient something like this. That means this is n1, this is n2, this is n1, and this is as a function of x. That means if you have a fiber which is having where the electromagnetic wave is moving through this region, then you need to find how many modes are basically supported. So you need to find uh, basically the V number. So and for this the V number is again 2 pi over lambda. I guess there is some issue. The call has ended out automatically, and So I have created a new meeting link because there was an issue with the previous one and somehow limiting the uh, time to only 1 hour. And if you're watching it on the YouTube, then you can just watch it freely. But if you were logged uh, in the live session, then I guess there's no way that I can communicate to you. Uh, Probably I need to check if I can do it. So let's basically get started again with the. Let me see if I can join. Okay, so I think the link is not exactly, working again. So I don't know, there is some issue. So let's continue with this. So we need to find the V number here. So V number will be exactly uh, because this is for lambda greater than critical wavelength. So you have the V number to be equivalent to 2 pi a over lambda under root of n1 square minus n2 square. So this will be exactly you need to find the this particular V number which will come out to be equivalent to 2.4, but you have V to be equivalent to 2.4405 times lambda c divided by lambda. And once you solve it, you get V to be equivalent to 1.86. So why this is the case? Because you have the cutoff wavelength given, and in that case, the V number and the cutoff wavelength are related to something like this. And and the exact answer is 1.86. That means the V is 1.86. That it doesn't mean it supports 1.86 of the modes. It means it can support one mode, or it can approximately support one mode, or maybe 1.86 modes means it's sort of a supporting single mode in the perfectly inside this particular slab. Now, which of the following is incorrect about the optical fibers? So for the optical fibers, if you have this is the core and this is the cladding. So this is the core, this is the cladding, and it is exactly gradient in the refractor index. If you draw this is sort of a refractor index profile for the optical fiber, and this is the front view of the optical fiber. Okay, and the electromagnetic wave or the waves basically electromagnetic wave propagates in this region, which is basically the core, because you hit it at certain angle, which is the critical angle. It undergoes total internal reflection and then it propagates into the transport direction. And for that, you know that this if this is core, this is cladding, then the refractive index of core will be greater than that of the cladding. That means basically what you have is this is absolutely wrong. So cladding is outside of the core. That is correct. works on total internal reflection. That's also correct. That means if you draw, this is the front view, if you draw the side view of the optical fiber, it looks like this, where this is the cladding, this is the core, and you heat it at certain angle, which is equivalent to the critical angle, it undergoes total internal reflection. But exactly at these points, there is sort of a wave decay, there is wave decay, decay, and that corresponds to basically certain losses in the fiber. But you try to minimize this evanescent decay as much as possible. Okay, so that is the functionality of this optical fiber. This is the simplest one. And now you have question 7, which is basically saying that a parallel plate guide has a space. It has a spacing A and is filled with a dielectric medium with relative permittivity epsilon r. The wave angle theta m for the first allowed mode. The wave angle is basically certain wave angle which is making an angle theta m. Okay, for the first allowed mode m equals to 1, we need to find the relation of it. Now, as per the condition that k cos theta m times a will be equivalent to m pi, which means it is going to support the the integer multiples of the wavelength. So it's going to support the integer number of wavelengths. So exactly the condition is that 2 pi. So if you write k as 2 pi by lambda cos theta m times a will be equivalent to m pi, you get this and this goes. So you have cos theta m times a is equivalent to m lambda by 2. So it's basically going to support the integer number of wavelengths, sort of a half wavelengths, whatever you call it. And given that you now have, for example, you now have epsilon r, you are going to replace the ks in this particular equation. You're going to replace it as k naught times square root of epsilon r, because it is k naught times n, and n is basically under root of epsilon r. So it will be cos theta m times a will be equivalent to m times pi. It is given that m is equivalent to 1, so you can write theta cos theta m to be equivalent to m pi divided by a under root a k naught under root of epsilon r. And similarly, the theta m, you can write cos inverse of this particular thing, which is basically part 2 is the answer of this question. So for the question 7, the part B is the answer of this question. Now for question 8, moving on to the question 8, what you have basically a parallel plate guide has a spacing of, you have a parallel plate guide, it has a spacing of 2 centimeters and it's filled with air. Right now the epsilon r is basically 1 because epsilon r is epsilon divided by epsilon naught, so this is equivalent to 1. The frequency is given as 30 gigahertz and the wave angle for the second allowed mode, this time m equals to 2. You have to use the same equation, but this time m is equivalent to 2. That means we need to find theta 2, which is equivalent to cos inverse of, it will be 2 pi over 2 into 10 to the power minus 2 meters, it's in meters, into k naught times under root of 1. What is this k naught? K naught is 2 pi over lambda. So it will be 2 pi over c into nu. So this is given, you put the values into k naught and you're gonna get the value of theta 2 to be equivalent to 60 degrees. So this will be the wave angle for the second allowed mode. So this will be 60 degrees. Let's check the answer. Yeah, it's 60 degrees. Now moving on to question 9. For the given data in the question A, the cutoff frequency for mode M2 is, we need to find the cutoff frequency for this mode, which is for m equals to 2. How are we going to find the cutoff frequency? You know that k times cos theta m a, which is equivalent to integer pi, integer multiples. That means cos theta m is equivalent to m pi over ka, the same equation we used previously. That means it's basically m pi over omega under root of mu epsilon, because why have you written it? Because you have K to be equivalent to omega over C, which is equivalent to omega under root of mu epsilon, because C is 1 by mu epsilon. So this is into A, so this will be m pi times omega under root of mu naught epsilon naught, and what has happened? Sorry. And mu r into epsilon naught epsilon r times the A. Once you use these values, what you are going to find is you have to find the omega, which is basically the cutoff frequency. So omega will be m pi c. Let's write it in terms of speed of light under root epsilon r times A. You get this to be equivalent to, so you have given this as 2, this is 3.14, this is 3 into 10 to the power 8, epsilon r is given. How much is it? It was 1, and A is also given, so you get omega cutoff to be equivalent to around, when you convert omega into 2 pi times frequency, you get frequency of the order of 15 gigahertz. So this will be in radians, so you need to convert it into gigahertz, so it will be 15 gigahertz. That's the answer of this question. Now, this is basically directly from the lecture, so I'm not going to discuss it. So which is the correct equation in the rectangular waveguide, which is basically, this is sort of looks like this is the equation which basically takes into account the propagation constant, the beta, which is basically the propagation factor. And the exact answer of this question is this part, which is basically showing you the EY component in a rectangular waveguide as a function of minus j, as a function of EZ and HX. Okay, and this is exactly covered in the lecture, so I'm not going to go through this question. So you need to basically derive it, and you can see the derivation in the lectures itself. So you need to solve the Maxwell's equation, and you need to find different components of the electric field vector, which is basically EY component, and accordingly you can basically relate it with, uh, I should say, the electric field components and the magnetic field components. So for now, this is about it, but I'm just trying to analyze if we missed something. I think we didn't. And but the essential thing is that if you understand the relation between, just what is happening, if you understand the relation between the waves in different interdisciplinary fields, then it's gonna make your life simpler. That's my advice. Because you see that these are electromagnetic waves, these are electron as a waves. Tomorrow you go higher and higher, you see, let me just show you. So right now, so if you have basically the waves, you have understood the waves phenomena in all different fields. It's gonna make your life simpler in the particular the physics, even mathematics, electronics, electrical engineering fields. It's going to make your life simpler, because here you talked about electromagnetic waves, you talked about electromagnetic waves, and you saw that a sort of the slab onto which the electromagnetic wave hits, it leaks to the other region and then it gets reflected. And if you somehow do a trick that you bring something very close to this particular region, let's say another glass slab or a prism or something, and it can get coupled and it can come out of the prism and it can go in the different direction. Okay, so but the amplitude will obviously be reduced. So if this was the initial amplitude, then the amplitude of this will be reduced, but this is exactly the same thing. So this is basically the evanescent mode getting coupled into the other medium basically. So this is exactly what you call as tunneling of the wave. And in electronics, I told you that this tunneling is similar in if you have a potential barrier, electronic potential, electrostatic potential barrier, and if this is A, this is X. If you have an electron wave coming in, it's gonna hit this, it's gonna hit this and it's gonna decay and it's gonna come out with a lower amplitude, basically the wave function. So if this is wave function, it'll be e to the power minus I omega t minus kx. Or you can write it, if you don't write it in terms of the time function, you can have e to the power minus I kx. And this will be, if this is a, then this will be approximately a by 2 e to the power minus I kx. Okay. And the point is that I mean a by two, or it will be some a by alpha, where a by maybe b. That means it's reduced by certain amplitude, where b is greater than a. So there's the essential thing. So amplitude is reduced, and but this is the same thing that internally this wave function will be some e to the power minus alpha x. That is the essential thing, and that means the electron hits it and it tunnels, boom, to the other side, and you are able to find the electron on the other side. In fact, that was not possible because the electron was in this energy level, and electron was at an energy level which was below this potential, V naught. So this E, electron's energy, was less than the potential. But it should mean that electron should not have gone to the other side of the potential, because it is just like you have a wall and you have a ball that is having this potential energy. So this is the potential energy, which will be the mass of the ball times the gravitational constant into the height of the ball from the floor. So this is height. So it will be the potential energy of the ball. And let's say this is some V, which is basically the, if you have certain object here, it will have potential energy V naught, okay, from the ground. That means if this ball has to go to this side, to the other side, then it has to go over this wall, and then it will come down. That means this mgh should be greater than V naught. Only then it will be able to go to the other side, to the side second, to the side two, because it's a ball. So it's because it's a classical object. And there is no other way. But if you miniaturize this ball, if you fine tune this ball, and if you make it, if it was an electron, and now if this is the potential for the electron, then this ball is basically this electron is also having certain wave function, which is basically a wave, and it's gonna decay through the wall and it's gonna appear on the other side. That means if this ball was a wave, just like an electron, it is a wave, but the wavelength is pretty huge, I should say. It's not, the dimensions are not of the same order as that of the electron. The de Broglie wavelength is pretty much, I should say, if you say, I should not say the huge. If you see for the electron, the de Broglie wavelength is h over under root of twice m energy. So for m for mass for the electrons is 9.1 into 10 to the power minus 31 kilograms. And for the ball, let's say the mass is, let's say, zero point 0.5 kilograms. And then accordingly, if you compute the de Broglie wavelength for the ball, it will be small because the denominator is huge. But here the electron's de Broglie wavelength will be huge because the mass in the denominator is small. So what does that mean? That electrons wavelength will be significant. This is insignificant wavelength for the ball, and as a result of that, the wavelength is for this is small. It cannot basically act as a wave. It cannot tunnel through this. It has to go over the barrier. But electron acts weirdly. It behaves as a wave, so it sort of tunnels at this point. Instead of going like this over the barrier, it tunnels and it exists on the other side because it's a wave, just as simple as that. And another thing that you noticed is that if you have now a step index, if you have a step refractive index, you had an index like this. This was refractive index n1, this was n2, this was n1. You saw that when you solve the Maxwell equation, you get different modes which look something like this. This is mode 1, this is mode 1, this is mode 2. Similarly, you have mode 3, so on and so forth. These are basically the distribution of the electric field in the space. It is basically A as a function of x, y, z, or if you are writing it only a single spatial direction, then it's E as a function of x. So this is basically telling you how electric field is varying as a function of, let's say this is z direction where it is through in the direction of propagation of it. So basically the refractive index looks like this. It's basically the slab. So this is z direction, this is x direction. So the first mode propagates like this, it then decays in the z direction. This is exactly how it propagates. So this is the wave, the solution of the Maxwell equation, and it decays with z. And if exactly you talk about the potential gradient for the electron. If you have the potential gradient for the electron, that means these are some sort of a potential wells for the electron, and these are different materials sort of layered together. Then you solve the Schrodinger equation, you get different levels of electron, n equals to 1, similarly n equals to 2, and n equals to 3, and so on and so forth. You get different levels for the electrons as basically the solution of the electron to the Schrodinger equation. And these exactly are similarly the wells. If you draw it in a three dimension, these look something like this. If you draw this well in a three dimension, it will look something like this. So, so this is the, let me draw the conduction band only. This is the conduction band of this material 1, and this is the conduction band of material 2. This is 2 material. This is again 2 material. Okay. And the electron wave function is looking something in the first, it looks something like this. So it propagates in this direction. And it's confined in this direction, and this direction it's confined. It cannot go to the, it's confined in x direction. It cannot go in the x direction. So that's why it's called as 2D quantum well, because electron can move only in sort of a two directions. It is confined in one of the directions. Okay, and that means electron can move only in two directions. That's the point. And because of it, what happens is exactly the electron is able to move through this well. It can move through this in this direction. The z direction can get propagated. And the other direction is confined. And because of this confinement, you have, once you solve the Schrodinger equation, you have different energy levels, which is basically the modes. So these are modes for the electrons. But these represent basically the energy levels of the electrons. That is similarly some sort of, these are like the modes of the Maxwell's equation. These are the solutions of the Maxwell equation. Okay, and which propagate inside this particular structure. And now again, if you now talk about the waves as, let's say, acoustic waves. Acoustic waves inside the material is basically something called as phonons. These are not particles, but these are fields which propagate in the medium, and these are sort of quasi-particles. It's not an exact particle, but you have the atoms, and if you just sort of give any sort of a stress to these atoms, then a sort of a wave, these atoms are going to move in a wave-like fashion. It's going to form a wave like this. So this is basically acoustic wave. And it propagates inside the medium basically. Okay, and just give me a moment. So these acoustic waves are basically propagating, and again these are basically propagating waves. So you deal it with in a similar fashion as you deal with the electromagnetic waves, you deal with the electronic waves, basically the electron waves. But this is basically exactly the it requires a medium to propagate because these are sort of a sound waves. So it requires a medium to propagate, and if these acoustic wave go into the terahertz region or beyond terahertz region, then it is basically what it gives rise to the heat transport in the system. So the heat transport is basically these acoustic waves, but in a very, very high frequency regime. Okay. And once you deal it with those waves, it exactly gives rise to the similar set of solutions. Okay. So that's the essential thing. I don't want to go into the acoustic wave detail here because it's a sort of a different topic, but this is my research field. So my research field exactly is at the domain of if this is so my research field deals with electrons, it deals with phonons, and it deals with photons. And this is my research field where I basically study all these three phenomena all together in the form of sometimes as a wave, sometimes as a particles, and how we can basically harness those wave particle duality for our certain applications. Okay, certain electronic applications, optical applications, commercial applications. So that's basically my research field. So that'll be about it, and I guess we are we are done with this today's session. And sorry for basically interruption, but it's not my fault. The Google Meet doesn't allow the meeting for greater than 1 hour. I have to inform this to the NPTEL, and this is on record so that they can see it. Hope to see you guys next week. Till then, see you. Bye bye. Hello, Purya.
Yes, sir.
Hello, Salam.
What's up?
Just wait a moment. Oh, shit.